Welcome back, students. Previously we have learned what exactly do we mean by divide and conquer strategy. We tried to solve certain problems using divide and conquer strategy. The different problems that we tried to solve were binary search, maximum problem, quicksort, and a merge sort problem. The next technique that we will be studying will be a greedy method, and the different problems that we will try to solve using greedy method are job sequencing, knapsack problem, optimal tape storage, and Huffman coding. So these are the various set of problems that we will be solving using this greedy strategy. So let's try to first understand what exactly do I mean by a greedy method. A greedy method is basically a very straightforward technique, a technique wherein we are given n number of inputs and we are supposed to retrieve some subsets out of these n inputs which satisfy some certain constraints. Now any subset of these elements, this is very important over here, n inputs is what is given to me, and from these n inputs I will be creating some subsets as solution. These subsets need to satisfy some constraints. Any such subset, any one subset, or any more than one or more than one subset that satisfies these constraints is what forms basically our feasible solution. We can have multiple feasible solutions for a certain problem, and one such feasible solution out of the set of feasible solutions, one such feasible solution that either minimizes or maximizes. The objective in greedy algorithm, the type of problems that we solve using greedy algorithm, the objective either is to maximize the result, maximize the output, or at times minimize the output. So whatever the objective is, that one solution which will either maximize or minimize is what you normally call as the optimal solution. Let's try to first define the greedy algorithm and the algorithm. Let's try to first define the greedy method and the algorithm for greedy method, and then we'll try to solve a certain problem using greedy method. The idea basically in this case is that we'll be working in different stages, and at every possible one stage we will be considering one input, and based on that one input we will decide whether this input should be part of the solution or not. So typically such kind of a problem is what form as subset paradigm. These are the kind of problems that form subset paradigms. Let's try to find the algorithm first, write down the algorithm for this problem, and then try to solve different problems using this algorithm. So the algorithm in this case will be in this case the A basically here carries the input, n is the number of elements, so A is the array that contains n inputs. Initially the solution is initialized to null, so nothing is there in the solution. That when we start solving this particular problem, the solution carries a null value, it's the initialization. We'll run a loop that will actually traverse. Let's run this loop essentially from 1, because we'll be considering the problem from 1, and the job of this loop is basically to traverse through all the inputs and see that which of these inputs can possibly become a part of the solution or not. So I'll be using a select function here. The job of the select function is basically to select this input, select one input at a time, and that input I'll be storing it in X, I'll try to calculate whether this solution, whether this input that I have just selected, can this be part of the solution or not. So feasible is a Boolean function over here. The feasible function that I'm using here in this case is a Boolean function that is going to return me a yes or a no. Typically these Boolean functions, they have two values, they either return you a yes or a no, a 1 and a 0. So it will return me that whether this solution is feasible, can this be part of the final solution or not. If it is feasible, then I will just put it in the form of a solution using a union function. The job of the union function here is nothing but to combine this solution to the existing solutions. And here we stop and we'll return back with the solution of the problem. So this is the algorithm for your greedy method. Let's try to find out, make use of an example of how exactly can we solve the problem using greedy technique, and what are the different pros and cons of using this greedy technique. Very simple, it's very simple to use, it's quick, that makes the implementation very easier, and it's easy to program. So these are certain characteristics. Why do we use these greedy methods? The idea behind your greedy method is that we try to find locally optimal solution with the hope that this locally optimal solution will actually take me to the globally optimal solution. So idea is that in a given set of inputs, we try to find, we use the typical greed, the factor of the greed we use to find out that which among these possible inputs that are given to me, which one among them is the best. So whichsoever input is supposedly best in the current scenario, we basically choose that particular element, and we take the hope that this element will actually take us the solution that's globally optimal. Let's take an example for this. Say I have to travel from location A to location B. Let's assume it's a 1,000 mile drive, or a distance of 1,000 miles. There are multiple ways with which I can travel from A to B. Let's assume I may be using bicycle as a means of transfer. I may be using a car as a means of transportation. I may be using a train even, or I may fly by air. Now, these are the different possible solutions that I can basically take. Greedy method suggests that let's find a feasible solution. So traveling 1,000 miles by bicycle may not be a feasible solution, or even traveling 1,000 miles by a car may not be a feasible solution, but traveling by train or traveling by air may be a feasible solution. Now if I need to find out that what is the optimal solution with respect to the cost, then traveling by train may be the optimal solution out of a set of feasible solutions. Or if I try to find in terms of time, then traveling by air may be a feasible optimal solution in terms of time. Having said that, is greedy method the best possible technique for solving such kind of problems? There are multiple other techniques. Say we have a dynamic program, we have branch and bound, with which we can solve optimal, wherein those problems wherein you have to minimize or maximize, we can use a branch and bound for them, we can use a dynamic program for them. What are the typical limitations with this greedy method? Is that it tries to locally optimize, get the locally optimal solution to solve a problem. Let me cite another example. Say for example I have to travel from A to B in this case, and there are various intersection points between A and B. So I may take this path, I may take this path, or I may take even this path. If I take this path, it costs me some 10 units. This may cost me 25, this may cost me 35. This from here may cost me 100, this 10, and this 15. If I take it this may cost 150, this may cost me a 5, this may cost me a 15, this may cost an 80. Let's take one more path, which, okay, we have that path of 150. Like here, let's talk 10 more. Now let's see how exactly will greedy algorithm work on this kind of a problem. So the idea here is that I have to travel from A location to location B, and these are the different costs involved in traveling, in traversing this path. Greedy algorithm here suggests that I should be selecting the path that is locally optimal. Now if you see locally optimal, I have three options with me. I may take a path that costs me 10, I may take a path that costs me 25, or else I may take a path that costs me 35. Now the greedy algorithm here suggests that take the one which is locally optimal. Locally optimal here is the least cost. It's a problem of minimization. Minimum costs is the idea we have to find out. Because of the greedy algorithm, I selected the one with the lower cost. But what I see is that once I make the second move from this place, the cost starts growing. And I have no option but to take the 80 here, which gives me a total of 10, 100 and then 80, which is a total of 190 cost. Let's see, had I taken the one with the largest cost possible, so if I had taken this 35, then it would have been 15 more, 5 and a 15. So we have 35 plus this is 40, that's 75. So what we can essentially see over here is that using greedy algorithm, I ended up with a path that's cost me more than other available paths. So there was another path available. Had I taken this path, it would have cost me only 75, almost 1/3 of the existing cost that I selected because of the greedy algorithm. So you may find out that there are instances wherein the greedy algorithm may give you the best possible result, the optimal result, but there are also possibilities that the greedy algorithm may not give you the optimal solution in these cases. Let's try to see different problems that we can solve using greedy method, and these problems, let's try to find out that how can we get a minimum, how do we get an optimal solution in problems when we have to either maximize or we have to find the minimum possible solutions. The first problem that we will check out with this technique is a job sequencing algorithm, job sequencing problem. We'll be looking at how do we solve job sequencing using greedy method. The problem statement for a job sequencing problem is that given an array of jobs where every job has a deadline and associated profit if the job is finished before deadline. So essentially the problem states that we are given a number of jobs and we have to execute these jobs. With every job there's an associated deadline within which we have to finish the job, and if we successfully finish the job within that deadline, then there's a profit associated with that job. We have a single machine on which we have to run all these jobs, and every job that we have to run on this machine, it takes a single unit of time. That means the minimum possible deadline for any job is 1. our objective in this problem is that how do we maximize the profit if only one job can be scheduled at one point of time. So the machine is a single machine. We have a single machine that's capable of running a single program at one point of time. We have multiple jobs to run on this machine, and every job has associated some deadline within which it has to be completed, and also some profits profits associated with the job which we can get if we are able to complete the job successfully before its deadline. Now the feasible solution here, possible feasible solution here is subset of jobs such that each job is successfully completed by its deadline. And what will be the value of this feasible solution? The value of this feasible solution will be sum of profits of job. Let's say job J here. And the optimal solution will be one feasible solution which has the maximum profit. So feasible solution with maximum profit. Let's try to understand this problem again. So essentially the problem states that there's a set of jobs. Let's suppose we have job J1, we have job J2, J3 up to Jn. So these are the jobs. These jobs I need to actually run on a single machine. So once I run them on a single machine, this machine is actually capable of processing one job at a time. Every such job, say this job has a deadline of 3, this job has a deadline of 1, this job has a deadline of 5. So that means this job has to be completed in 3 units of time. So every single job, remember that every single job needs just 1 unit of time for its completion. But the fact is that even this job, even if it's completed, it can wait for 2 more units before it can be completed. Say, if example, if this is a slot machine wherein the jobs are working, and job 1 here has a deadline of 3, that means in any of these 3 slots I can fit this and process this job. It's not necessary that as soon as it arrives I need to finish the job. No, it has that flexibility that it can basically wait for at least 3 units of time, whereas job 2 comparatively cannot wait. So since it is 1 unit deadline, because of this 1 unit deadline I need to finish it without any wait immediately. But in the case of J3 we have 5 deadline, that means it can wait, it has the flexibility of waiting up to 5 units of time. The objective in this case, in this problem, is that I have to maximize the profit if only one job can be scheduled at one point of time. What are the different possible solutions? So let's assume if I run J1, J3, J7 and J9, that subset, if I run that subset, that may form one feasible solution, or a J2, a J5 or a J7, that is another subset that is possible feasible solution. There are multiple feasible solutions such that, so those subset of jobs such that each job is basically completed by its deadline. What will be the value of that one subset? That value will be sum of profits of jobs. Say, for example, if one subset is my J1, J3 and a J7, so the profits associated with them, sum of the profits of these jobs will be the value. And what will be the optimal solution? Given these some feasible solutions, say I have 3 subsets of feasible solution or a 4 subsets of feasible solution, the one feasible solution which has the maximum profit will form the optimal solution. Let's take an example for this job sequencing problem and understand how exactly does it work. Let's try to solve this one job sequencing problem. So if we see the problem, we have 5 jobs in this problem. So I'm using this index to count how many jobs I have. I have 5 jobs here, 1, 2, 3, 4, 5. These jobs can be identified by their job indexes, so J1, J2, J3, J4 and J5 are the different jobs we have. Each job has its own associated deadline. So this job needs to be finished or completed by 2 units of time, this in 1 unit of time, this 3, 2 and 1. And every job has its own associated profit. So job J1, if completed within its deadline, will earn us a profit of 100. Likewise, J2, if completed within its deadline, will earn us a profit of 60. For J3 it's a 40, J4 it's a 20, and J5 it's a 20. What you need to remember over here importantly is that if these jobs are not sorted in descending order of their profits, then before you proceed, you actually need to sort them in descending order. So the job with the highest profit should be the first job in this case, and followed by the other jobs in this case. So since my problem in this case is already sorted, so I need not to worry about the sorting of profits. Next is that I need to find the maximum deadline value. I'll come to this, what I mean by this deadline value. If I check the deadline values associated with different jobs, so this is a deadline value of 2, this is a deadline value of 3, 1, sorry, the deadline value of 3, deadline value of 2, and deadline value of 1. In job sequencing problem using gradient method, we will be selecting the deadline value that has the highest value. So if I see a 2, a 1, a 3, 2 and a 1, so the value that I will be selecting here, maximum deadline value, that will be my 3. Given this deadline value 3, the highest deadline value whatsoever is in your problem, in my case it's a 3, so we will be assigning different slots. So we have 3 slots for running jobs on this machine. So the slots will be like this: 0 to 1, 1 to 2, and 2 to 3. So these are 3 different slots that are there on my machine, and these jobs I can run on these in these different slots. So typically, how do I solve this particular problem is, given that we have 3 slots of time, let's find how do we solve this using greedy method. So initially, the solution set of jobs contains is initialized to null. That means there is nothing in the job solution set, the subset that I'm going to create out of this. And no job has been yet assigned to the machine. The machine is not running any problem right now. So the first job that I consider is the job 1, J1. Remember that the J1 I'm selected because it has the highest profit. The profit of 100 is associated with this job. So these are my slots. I have a 0 to 1 slot, I have a 1 to 2 slot, and I have a 2 to 3 slot. Now, if you see the job J1, in this case, my job J1 here will be assigned to the slot 0 and 1. Since the job J1, the deadline value associated with job J1 is the 1 unit of time, so I can the only possible slot for J1 in this case is the first slot. Now remember, this is very important in this case, that if the J1 had a value different than 1, if say J1 had a value of 2 or a J1 had a value of 3, then I could actually defer this, keep this slot empty and put it maybe in the second slot or the third slot, preferably in the third, then in the second, then in the first, because that way I can give more time to other jobs that can basically fit here, that cannot wait. Since if it was the case that J1 had a value higher than 1, then it could basically, it had the flexibility of waiting for other jobs to be accommodated. Since in this case that's not possible, so I'm assigning job 1 to the machine, and I have not earned any profit yet. Concurrently, the status of the machine right now is that the job job J1 has been already assigned, and it has been assigned in the set or slot 01. And now I'm considering job J2. So this is the next job I'm going to consider in this case. Now if you see that my job J2 has a deadline of 2, and I cannot put it here because the slot is already occupied. So and I cannot put it here because this is a deadline of 3, so I cannot definitely not put it there. So the only deadline that's possible where I can fit this job is this position. So I'll assign it to the slot 1 and 2. And in the meantime, I have finished this job, so the profit earned from J1 is my 100. That's the profit associated with job J1, that profit I have already earned. In the next iteration, so we have already considered job J1 and job J2, so the solution set here contains job 1 and 2, and the assigned slots that we have already occupied is slot 1 as well as slot 2. And next job that I am considering is my job 3, J3. Now J3, you can find in this case has a value of dead value of 2. The deadline associated with job J3 is 2. Now this slot that's been already occupied, this slot that has already been occupied, the only free slot here J2 is already occupied, the only free slot is J3, but the deadline associated with job J3 slot is 2 to 3 is only free slot, but the deadline associated with J3 is 2. Since this 2 is already occupied, I cannot fit this job in the machine, so I will simply reject this particular job because I do not have a free slot of time wherein this will fit, this job will fit. And the total profit earned in this case is 160 from the J2, so that gives me 160 profit. Next job that I am going to, the solution set still contains 1 and 2, and the slots 0 and 1 and 1 and 2 are still occupied, and the job that I am going to consider is J4. Now if you see that J4 has a deadline of 3, since it is a deadline of 3 and I have a free slot in this case, so I will be assigning that free slot to job J4. So the assigned slot in this case will be 2 to 3. And the profit earned still is 160 because the previous job earned me nothing because that job got rejected, so that did not earn me any profit, so I rejected that. Now I can see that the solution set contains 1, 2 and the 4 job that I just assigned. The slots that have been occupied is first slot, slot from 1 to 2 and slot from 2 to 3. All the 3 slots have been occupied, and the job I am considering is the last job, that's J5. Again, if you see in case of J5 that the deadline of the J5 associated with the J5 is 1, but I can find out that already the slot 1 has been occupied, slot 1 to 2 has been occupied, slot 2 to 3 has been occupied. Either way these two don't matter because the deadline is 1, but this one is already occupied, so I will just reject J5. And the profit earned, total profit earned is 180, given that J4 fetched me a profit of 20, so the total profit in this case is 180. So what essentially we have what we did over here is that we considered one job at a time. Jobs with the highest profit we actually consider them first, and this way we were able to assign 3 jobs to the processor. So the optimal solution, possible optimal solution subset is the final subset that we get, that will be job 1, 2 and 4. This is how we actually solve a job sequencing problem using greedy method. Next, in the next class, we'll be learning the knapsack problem. How do we solve a knapsack problem using greedy method? Take care. Bye.
Thank you.